yesterday we learned all about indefinite integrals. It was, you had the integration symbol, you had some kind of function, and we had a dx, and we knew that that was antiderivatives. I'm not really actually going to talk about the difference between these two. Just know that definite integrals we are going to do next week. Okay? I don't really want to spend any more time today about talking about that. What I want to talk about instead are the difference between particular solutions, differential equations, and general solutions. I want to talk about the difference between those things. All right, now, looking at example number 1, okay, what type of equation is this? I'll give you a hint. You have 3 options here. Which one ends in equation? Differential. What does differential mean? It's a derivative. Okay? So, isn't y prime a derivative? All right. So, one thing we are going to do is we're going to not use y prime notation. What's our other way of writing y prime? I'll give you a hint. We could write it like that, but dy over dx. Now, let me explain just a little bit of why we're using dy over dx. Y prime, I know. Try teaching that to people whose English is not their first language, and that's a lot harder. But the reason is because y prime looks a lot like y. But is it the same as y? Not at all. Okay? They're related, but they're not the same. So we write this for, that's just one reason. Okay? And I'm going to lead you guys through a process. And the first step is going to be replace y prime with dy over dx. Okay, this is going to be our process for solving these equations. And we'll get to the integration part in a minute. Okay, the next thing we're going to do is separate the variables. Okay, so what does that mean? It means that we're only going to have y's on the left, and we're only going to have x's on the right. So one thing is 3x squared minus 1 is exactly where it needs to be. Okay, dy is where it needs to be. Dx, on the other hand, is out of place. So what could we do with the dx? Multiply it over to that other side. So that's what I'm going to do, and then I'll leave that dy right there. Okay, so that's called separating your variables. For everything we do today, and in fact this entire chapter, it's as easy as multiplying the dx to the other side. In the future, it will be a little bit more complicated. This step will be. But we'll get to that. That's like weeks. That's like over a month away, I think. All right, so let's do the next step. What does the D stand for? What do you think? Derivative. It technically stands for delta here. Like, remember, delta y over delta x change. But if you think of it as derivative, that's not a bad thing. So I'm going to go with you on this and say this D means derivative. And so we are going to anti-derive both sides. And I'm going to go ahead and start using the word integrate more often. So we're going to integrate both sides. Okay? So what is the antiderivative or integral of the derivative of y? Just y. So this is how all the problems are going to work out. Not in the future, but for now, this is how they're all going to work out. We're going to multiply dx to the other side. We're going to antiderive. The left side is going to just be y. The right side, this is what we learned how to do yesterday. This is called an indefinite integral. So we would take the coefficient. We would say it's over something. We would write the x. And what would we do next? Add 1 to that power. You get 3, and then put that same number in the denominator. Okay, and I'm going to do the same thing here. Minus 1 over. Now there's no x here. So what was the power? 0. So what is the power now? 1. The power was 0. Now it's 1. Put that down there. And don't forget plus c. We're not. We're going to clean it up a little bit because we're going to need to do something with this in a minute. If this was all we needed to do, just you could leave it like that. So 3 over 3, that's obviously 1. We're left with x cubed minus x plus c. Okay, and this is something called a general solution. I'm going to abbreviate here because I don't have a lot of room. Feel free to write that out, general solution. When you have the plus C, that's a general solution. Okay, and that's what we did yesterday. I'm going to add on one more step, but it's actually not really that hard at all. Okay. All right, so I want to explain to you what this even means. So I'm going to scroll where we can still see our answer and still see all of these. Okay, all of these curves, and by the way, I'm giving you this graph to explain it. Next time we do this example, I'm not going to give you the graph, and you don't have to come up with the graph. We're going to come up with an algebraic way to do this. But for now, all of these curves represent y equals x cubed minus x plus some number. Okay? This one is plus 5. I'm not going to list all of them. I'm going to see if you can figure out how I'm getting this. The bottom one, did you figure it out? It is the y-intercept. Does that make sense why the last number would be the y-intercept? Because if x is 0, the last number without the x by it would be it. So you can kind of see that's how I did it. All right? So we could have listed them all out. We really don't need to do that. Okay, so then what we need to do is, in order to make this go from general to particular, we have to have been given something called an initial condition. Okay? Initial condition really just means a point. And it's always going to be written in function notation. So f of 2 equals 4. The way we're going to rewrite that is the point 2 comma 4. Okay? Where the 2 is representing an x and the 4 is representing a y. You don't have to write it like a point, but it's okay. You don't have to write it as a point, but what you do have to recognize is that the number in the parentheses is an x and the equals number is a y. We've seen this before. This isn't the first time we've seen this. So, do you see the point on the graph? It's kind of like bolded right here. This is right here, the point. So if I kind of, and I'm going to do this, you may on your paper want to highlight this or use a colored pen or something. You don't have to, but so already based off of this graph, I know what the C should be. What should, this is a tongue twister, what should C equal?
-2.
-2, okay. So we came up with it this way, but again, this is not going to be provided in other problems. So we need to come up with an algebraic way of finding C. It all hinges on this information. Okay, let's go up really quick and let's put in this last step. And you can only do this if you have an initial condition. So we are going to plug in the initial condition, which is really just a point, to find C. So we don't always do this. We just do this in the cases where we have an initial condition. Okay, first, let's go ahead and just rewrite this so that when you're looking back at your notes, you don't have to look at both parts, and just so we have it. So we've rewritten the general solution. Okay, remember over here I said that the 2 is getting plugged into x and the 4 is getting plugged into y. So let's do that. I know my y's and 4's look an awful lot alike. So we plug in those numbers, and the rest is just adding and subtracting and number crunching. So 2 cubed, that's 8. And you should be able to do all this without a calculator. So I get 4 equals 6 plus C. You're solving the equation. And you solve it down until you can figure out what C equals. So in this case, C equals -2. We kind of already got a sneak preview that was going to be the answer. But here's how you algebraically find it. You still need to do one more thing. You need to write your particular solution. Okay? And that is y equals, and you're going to write your same y equals, but instead of plus C, we're going to write -2. So That's the difference between general solution and particular solution. And you need to know that because in the directions, it's going to tell you when to do which one. Okay, so we got 3 examples we're going to kind of go through. And they're all polynomials, so we're not even going to do any trig today. We're just going to focus right now on the steps. Feel free to go back in your paper to remind yourself of the steps. Okay, so find the general solution. Right now, they've already put it into dy over dx, so I don't even have to do that first step. But what I do need to do is move that dx over to the other side. And I probably should rewrite this. How could I rewrite that? Yeah. That over x squared can change to a power of -2. Do I need the 1? No. I wrote it. You didn't have to write it. Okay, these d's tell us that this is a derivative. How do you undo that? You integrate both sides. The left side, super easy. Just y. The right side, this is where we got to use the stuff that we learned yesterday. So -1 over, what would be the new power in this problem? -1, because remember we're adding 1. Don't forget plus c. And I'm going to clean this up just a little bit because I know I have another step to go. So I'm going to cross off these -1s, and I'm also going to rewrite this. You do not have to do this. You could have left it as x to the -1. I know, though, with number crunching, this is probably going to be a little easier to work with. That's a preference, though. So let me box this. This is my general solution. And this last step right here is what we focused on yesterday. Okay, particular solution. This is the new last step. You have to be given an initial condition. The biggest mistake made here is not knowing which number to plug in for x or for y. The number in parentheses is always x. Just think f of x. So 1/2 goes in for x, 3 goes in for y. So I'm going to do 3 equals 1 over 1/2 plus c. Well, what is 1 over 1/2? 2. So c in this case equals 1. And I need to go ahead and write my final answer as 1 over x. It would be totally okay if you had written it as x to the -1. But instead of plus c, we got to write what c actually equals. Plus 1. That's the particular solution. Okay, we're sticking with polynomials. We're not dealing with any trig. I'm not saying never, but for right now, let's just learn the process. Okay, so I'm going to keep the answers kind of showing there in case you're still doing that. But what would be the very first step on 3? Change that y prime to dy over dx. Do you think you know the next step? Multiply by dx. And it's okay if you don't put this thing in parentheses, but it really kind of should be because the whole thing, you know, is multiplied to dx. And then integrate. Remember, if there are d's in your problem, you still need to integrate. I want you to try to finish this one, both the general and also plugging the numbers in for the particular. Okay, what was the antiderivative of 6x squared? And go ahead and simplify it for me. 2x cubed. You should have had the 6 over, and then x cubed, 6 over 3 would be 2. Okay, what about the antiderivative of -1? Negative x. Okay, this right here is your general solution. Alright, so 0 gets plugged in for y, while 3 gets plugged in for x. And this number turns out to be kind of weird. What'd you guys get, those of you that finished it? Negative 51, which seems like a big number. You might have thought that you did it wrong because of that. Okay. All right. So what I added on, we're doing okay with that? Yes. Polynomials we like? Yes. Okay. So how is 4 different? There is a second, yes. I didn't. This is a minus. My pen cut out. Yeah. Okay, so this is an F double prime. So we got to kind of really think back. What does F double prime look like in the D? Like D what? D squared y over dx squared. I know that seems weird. We talked about y. I'm not going to get into it anymore today, but you'll kind of see this work out here. Okay, so that equals 6x. And we know something different is going to happen here, but we're just going to follow the steps. We need to separate the variables. So keep the d squared y on the left. On the right, move that dx squared over. And then the d's there tell me that those are derivatives. So I am going to integrate. Now listen to how I'm going to explain this. This is the second derivative. So if I integrate the second derivative, what will I be left with? The first derivative. So that's going to change into dy. Okay. What is the antiderivative of 6x? And go ahead and simplify it. 3x squared. I can easily check this by deriving. 2 times 3, that's 6. Subtract 1, I'm good. And I need a plus c here. And again, I still have a dx there. Okay? Now, this is kind of strange, so just hang with me here. All right? I need to use this initial condition now. I can't wait to the end. But what is f prime representing? Dy over dx. So for just a minute, I'm going to move that dx over. And now this is the same as f prime. So which number can I replace this left side with? 13. And the x, always the number in parentheses. And there's still some stuff left. We're not done with the problem. But we need to go ahead and find this value. So what does that end up being? C equals 1. Okay? So what I'm going to do is I'm going to rewrite this, but instead of plus c, I'm going to write a 1. So dy equals 3x squared plus 1, and there's a dx over here, and probably I should really have parentheses there. But it would be okay if you left the parentheses off. That's not something you're going to get counted off for, okay? Okay, I still have dy, so what do I still need to do again? I need to integrate, I need to take the antiderivative. Now, from here, this is very similar to the ones we just did. So on the left side, I should just have y. And what am I going to have on the right side? What's the antiderivative of 3x squared simplified? X cubed plus x plus c. Okay, so the million-dollar question is, I already found c, so can I just plug in a 1 here? And the answer to that is no. Here is why. They are different. Okay, so what I'm not requiring you to do, but you know, when you start using the second initial condition, one thing that some students might want to do just to distinguish is put subscripts. Okay, you've seen subscripts before. C sub 1. Okay, that's that C. Okay, C is fluid. It's changing all the time depending upon the initial condition. So what would we call this C over here? C sub 2. So then I'm going to plug in this initial condition. So I'm going to plug 4 in for y and plug 1 in for x. So what is C sub 2? 2. So we can see that they are not the same. So my final answer, my particular solution for this entire problem is y equals x cubed plus x plus 2. Now, we did a lot of steps, and there is tons of chances that I might have made a mistake. So here's how you check your work and know 100% that you did this right. If you plug in a 1, will you get 4? If you plug 1 in for x, will the result be 4? Yes. Okay, if I take the derivative, I will get 3x squared plus 1. And if I plug in a 2, will I get 13? And I'm not showing all this, but you could easily go off to the side and do this. Yes. And if I took the second derivative, would I get 6x? Yes. You can check your work and know for sure you're right on these or wrong.